Hello, student. Welcome to this topic of virtual labs in physics. So, in this session, I am going to explain one experiment in electricity and magnetism, which is the Quincke's method. The Quincke's method to determine the susceptibility of a given paramagnetic material is that if you don't have the setup, you can do the virtual lab. So for that, you have to go to again Google, and in the Google type the virtual lab. Virtual lab is here. So when you type it, virtual, let's say it goes to the website. MHRD virtual lab is the website. So click on that, then go to the virtual lab. So this website opens. And in this website, you have to go to the physical sciences where the physics related experiments are present, and scroll down. And here is electricity and magnetism is the branch of physics where we have to do the experiment. And after clicking that, you will click on the list of experiment. These are the list of experiment on electricity and magnetism. So many are there. And this eighth one is the Quincke's method. So click on the Quincke's method. The Quincke's method opens up. And this Quincke's method is used to determine the volume magnetic susceptibility of manganese sulphate solution at different concentrations, or you can do at single concentration, whatever it is. So this manganese sulphate is chosen because this is a paramagnetic material in the sulphate form, and it's a solution you will have to prepare according to some molarity. I will explain that. So the aim of this experiment is to determine the volume magnetic susceptibility of this magnetic sulphate solution at different concentrations. Okay. Click on the theory, related theory opens, Quincke's method, and so this susceptibility is a ratio of magnetization in the material to the applied field. And that we are calling as the susceptibility, and it is in a dimensionless quantity. So this indicates the degree of magnetization of material in response to an applied magnetic field. That means if for a given material, for a given applied field, if you have a more magnetization, then it shows that the material is responding more to the applied field. That means the susceptibility will be a higher value. So higher the value of susceptibility, the material respond more to the applied field. So that is the meaning. So susceptibility is such a quantity, so that gives the degree of that indicates the degree of magnetization of a material with respect to the applied field. So magnetization, the degree of magnetization means to what extent the magnetic dipoles are aligned in the field direction, gives the degree of magnetization. So that means if all the dipoles oriented along the field direction, then we can say that the degree of magnetization is higher. So that kind of meaning it gives. So in this equation, this M is the magnetization, means the alignment of the magnetic dipoles in the field direction, and H is the applied field. And this is also equal to mu or minus 1, where Mu r is the relative permeability of the material. So permeability of material is another parameter in the magnetism that gives the idea about how much the material is permeable. That means allows the magnetic flux to pass through the material. So that such a quantity is called as the relative permeability. And so this Quincke's method is used to determine the magnetic susceptibility of many liquids or aqueous solutions and liquefied gases. And here in this virtual lab, the manganese sulphate solution is used, which is a paramagnetic material at different concentrations. The experimental setup for Quincke's method is as shown below. And here a special type of tube is used. It's called as the Quincke's tube. And this is a U type of tube it is. So here the manganese sulfate solution under investigation is placed in a vertical U tube with one limb wide bore and the other with narrow bore. So this is the one limb. This is another limb. This is a limb with wide bore. This is the limb with another bore. The narrow limb is placed in between the pole pieces of an electromagnet. So here what you are looking, these two are the electromagnets. And between that, this narrow limb is placed. It should be noted that the surface of the liquid in the narrow limb must lie at the line of center of the pole pieces. So initially you have to adjust the height of the Quincke's tube in such a way that this wide bore is outside the magnetic field, but this narrow bore is exactly at the middle of the magnetic field, and that's why the initial height of the solution in this Quincke's tube is very important, and you have to adjust the height of the solution in a narrow bore in such a way that it is exactly at the middle of this what is that electromagnets. That means it should be aligned with the axis of these two electromagnetic poles, which is passing through the electromagnetic poles. So that is the initial adjustment what you have to do. So what happens here, when the current is switched on, a strong field is appeared at the upper surface of the narrow column, while the lower portion will be in a state of completely weak field. Hence, a force will act upon the column, and if the liquid is paramagnetic, it will rise. So what happens here, when we are applying the strong magnetic field with the help of these electromagnets, and since this magnet sulfate is a paramagnetic material, the characteristics of the paramagnetic material is that it always moves from a region of lower magnetic field to the region of higher magnetic field. That's why it is attracted. The solution in the tube is attracted by the magnetic field, and because of that reason, what happens? The level of the or the height of the solution inside this Quincke's tube in this side goes up slightly or gradually it rises up. So it's what happening. So when you gradually increase the magnetic field with the help of these electromagnets, the rise in the liquid will also be a gradual one. So what happens? This is the equation for the susceptibility connecting the various parameters. So it is psi 2. Actually, x is written, but it is not x. We have to use the symbol psi to represent the susceptibility. So the psi 2 minus 7 is equal to 2gh into rho minus sigma upon mu naught into hm square. So in this equation, x2 and x1 are the susceptibilities of the solution and air. And this rho and sigma are the densities of liquid and air. G is the acceleration due to gravity. H is the rise in the surface of the liquid in the Quincke's tube. And hm is the final field applied. So this is the equation. Then they taking the susceptibility of air approximately equal to 0. So this x1 goes to 0 and this equation 2 becomes like this. So actually here what we should also do some correction to this equation 3 is that this has some more parameters like this density of air. So the density of air is taken as a zero, very less as compared to density of this liquid, and this quantity mu naught is the absolute permeability of the free space, that is equal to 1. So you can neglect this mu naught and sigma in the equation 3. Then what happens? This becomes psi solution is equal to tau gh into rho, as you are dropping this divided by hm square, because mu naught is also dropped. So that is the final equation what we are going to use for the calculation of susceptibility in this experiment. So this is the theoretical part. Next, we will go to the procedure part. Procedure part, briefly I will explain. This contains two parts. One, we have to calibrate the electromagnets. So for that, this is needed. Magnetic field versus current part we have to do. And in the second part, we are going to place the Quincke's tube and we have to do the experiment. So two parts are there. So in this experiment, to change the current, one slider is available. To change the molarity, another slider is available, and that we'll see. I will show you. And remove or insert bar remove button is there. So when you press it, the tube is either inserted or set or removed. And to where is the voltage or current, the knobs are also there. I will show you how to do it. So in the procedure, what we have to do, first we have to calibrate the electromagnets. For that, this column is required. So I will directly show you. This is the column to enter the readings, and our modified column is there. I will show you, because now in this experiment we are not only calibrating the electromagnets, but also we are determining the susceptibility of the manganese or manganese sulphate. That's why the table changes. So that's why I will move to the simulation part. So when you click on the simulation part opens up like this. And once this window is opened, so you can see the experimental setup of this Quincke's method. So in this picture, you can see the huge two huge electromagnets are there, which are used to apply the strong magnetic field. And this is the stand to place the Quincke's to place the probe or the Quincke's tube. And here ammeter is there, so that shows the current, how much of current is passing through this electromagnets. And here is another equipment which is used or which is kept here to measure the what is that magnetic field? How much of magnetic field is there? So let us start the experiment. So for that, you have to click here, and the first part we have to choose. So now we have chosen the first part. That means we are going to calibrate the electromagnets. Then you click on the insert probe. So when you click on the insert probe, you can see here this probe, Hall probe. It is called as the Hall probe. So this probe is is inserted to the middle of this electromagnets in between, so that it measures the magnetic field created between these two electromagnets. And now what we have to do, we have to change the current and note down the magnetic field. So right now, this is the current slider button. So by moving this current slider button, you can change the current, and at the same time, you have to note down the magnetic field in the Gauss meter. So this magnetic field in the Gauss meter gives the magnetic field in kilogauss. Remember, it gives in kilogauss. So right now you can see the current applied is the 0.5 ampere. So for this applied current, the magnetic field created between these two electromagnets is 0.113 kilogauss. Next, I will change the current here. Click on this current slider button, and you can move this current slider button like this. Now the current in the electromagnets is 1 ampere. So you can see the magnetic field is raised. It is 0.227. And next you move to this position, and now it is 1.5 ampere. The current is the magnetic field is 0.340 kilogauss, and increase to 2. You can see 2 is the current, 2 ampere is the current. Magnetic field is 0.453. Next move 2.5 is the current. Magnetic field is 0.567. And next 3 is the 3 ampere is the current. 0.680 is the magnetic field. 3.5 is the current. 0.7 and 3 kilogauss is the magnetic field. So in this way, by changing the current, it is 4.55 up to 5 ampere you can go. So apply the current in steps of 0.5 ampere up to 5 amperes and note down the magnetic field. Okay. So once you note down the magnetic field, when you do this part, you have to plot a graph that I will show you later to calibrate the electromagnets. Okay. So first part of the experiment is over. Now click here in the setup, select setup knob, and as the first part is over, select the second part, Quincke setup. So when you click on the Quincke setup opens here. So in the Quincke setup, what is there? You can see here. You see, Quincke's tube is now inside this electromagnets. So this is the Quincke's tube. The narrow limb of the Quincke's tube is kept these two electromagnets, and the height of the what is that this MNSF or solution in this Quincke's tube is seen through a traveling microscope. So for that, a traveling microscope is kept here, and you have to focus this traveling microscope to the height of the solution, and this is seen like this. This is what you are observing is the height, the liquid level in the Quincke's tube. Okay, so that you can sharpen it. You can see here, this is the meniscus. So the meniscus is not so clear. To adjust the meniscus, this knob is given. For example, I will show you. You can see it is gets blurred, more blurred. So you move this side so that it becomes more clear and clear. And now you can see it's very clear. It is still clear. Okay. Because if you are moving ahead again, it gets blurred in this way. So only at particular position of this knob, the meniscus will be seen clear. Now you can see it is seen very clearly. So what happens now? Now once you focus the trolling microscope to this height of the liquid in the Quincke tube, next you have to move to the current slider knob, and the current slider knob is here. So you have to first give the lowest current. You have to start with 0.5 current, 0.5 amperes of current. So when you apply the 0.5 ampere of current, uh, there will be some changes in the liquid level in the Quincke tube, and molarity also you can choose for one set of experiment. And right now the molarity of this solution is 0.5 m. Next, we have to adjust this horizontal crosswire of this trolling microscope to the liquid level. For that, we have to adjust this another knob is there that we have to use to adjust the uh, knob like this. You can see. So you have to adjust the horizontal crosswire to the lower meniscus, bottom of the lower meniscus of the level. So now you can see here, the bottom of this meniscus is focused to the horizontal crosswire of the turning microscope. And now we have to take a reading. How you will take the reading? You have to click here on the trailing microscope. So the scale of the trailing microscope opens here. So the list count, all those things you can do here. You just like using the vernier. And now you can see here, this is the reading. It is the zeroth of the vernier is there. So to note down the main scale reading, MS reading, this zeroth line indicates what line on the main scale is the MSR, main scale reading line. Now it is 13 is there, it is 12.5, 12.6, 12.7, 12.8, 12.85. 12.85 is the main scale reading. And here you can see, and then we have to note the CVD, means coincided vernier divisions. That means 50 divisions are there on the vernier. Out of 50 divisions, at least one line will be coincided with the main scale reading, and that we have to search, and that gives the CVD, coincided vernier division. For example, you can see here this line after 10th here. Here we can see it is 10, 11, 12, 13th line is very clearly focused or coincided with the main scale reading. So CVD becomes 13. In this way, we have to note on the reading each time. So once the reading is taken, again click on the that vernier part. So you will come back to this picture. And now you increase the current. Now I applied 0.5 ampere of current and took one reading. Next, increase the current to 1 ampere. So 1 ampere current is shown here. And again click here. You will see the graduation line. So you will magnified image of this trolling microscope scale is seen. And I can again look at the zeroth line of the vernier calipers to note down the MSR reading. Again, you can see here it is still 12.85, and only some changes in the CVD will be observed. there will be no much change in the MSR value. Slight change in the CVD value will appear. Now you can see here this line or this line. So means 13th, 14th, 15th line, nearly 15th line is coinciding with the CVD. So in this way, slight changes in the CVD value you have to carefully detect and note down the reading. So repeat this experiment for different values of current. So for again, you click here and increase the current and focus the this meniscus again for each current carefully. Now it is focused and note down the reading by clicking here like this. Again, this graduation opens and note down this again. Note down the CVD and get the total reading value. So again, click here, go back and increase the current and adjust the height and take the reading. So in this way, you have to go to up to 5 amperes of current. You have to go to up to 5 amperes of current. You see very clearly now I have given the 5 amperes of current. The liquid is raised to this much. So it's very clearly shows that as you increase the current, and the height of the liquid in the Quincke tube goes on increasing in step by step. Okay. So now the experiment part is over. This much you have to do, and now I will analyze the results. For that, we have done the experiment here. Already we have taken the readings. And you can see here, I will go to the sheet 1, the data sheet. So this is the now the tabulation for this experiment. One column is required for the current. The second column is used to note down the magnetic field. And next third column, you are squaring the magnetic field, means H into H, means square of this magnetic field gives this column. And height in the Quincke tube is noted down for every current, so that is noted here. So this is the micrometer reading or height of the liquid in the Quincke tube. So this is the complete tabulation column, tabulation required for this experiment. And now what happens? This is the formula, modified formula to determine the susceptibility of the experiment. So psi is equal to 2 into rho into G into H upon H square. So this H upon H square is a slope of the H versus H square graph that we have to determine. So here first two graphs we have to plot. So this is the first graph. It is the current versus magnetic field. So this, so that is a straight line. The straight line indicates that the magnetic field produced in the electromagnet is a linear function of the current applied. So that thing is verified. And next, chart 2, another graph you have to plot. That means this one, H versus H cross H square. H square versus H. This another graph you have to plot. So that is also plotted. So H square is plotted along the x-axis. Micrometer reading H is plotted on the y-axis. So we can see here it is nearly a straight line, not exactly. It's a nearly a straight line. And for this straight line, we have to determine the slope. So to determine the slope, we have dropped the perpendiculars to the y-axis and x-axis. So you can see here these two perpendiculars meet the line here and here. from that point, the horizontal lines are drawn. So this is the delta H, and this is the delta S squared. So the slope is what is that? The slope is delta H, delta small h divided by delta H squared. So that is the slope. So slope is also determined. So 0.007 is approximately gives this much small h value, delta h value, and 0.25 is the value of delta h square. So that is the slope. And come to the calculation part. So I have calculated here using this modified formula. So psi is equal to 2 rho g into slope. So I am substituting the values here. So 2 rho means it is density of the liquid, that is taken as 1.30 into 10 to the power 3. So it is 1.30 gram per centimeter cube, but we are needing in SI, so it becomes 1.30 into 10 to the power 3. And G is a 9.8 into slope is this much. That means it is the 0.007 divided by 0.25. Value of that is 0.028 into 10 to the power minus 8 comes, because we have to convert the slope into SI unit is there. I will show you why it is. Because here 0.007 is in centimeter is there. So 10 to the power minus 2 comes here, and 0.25 is the value of h square. So it is since h is in kilogauss, so it gives 10 to the power 3 into 10 to the power 3 means 10 to the power 6 is down. And here 10 to the power minus 2 is there when you convert this centimeter into meter. So this 10 to the power plus 6 goes up. So it becomes 10 to the power totally minus 8. That is why that power comes here in the calculation. So this 10 to the power minus 8 comes because of the conversion of the CGS to SI unit. So when you calculate all these things, the value obtained is 0.713 10 to the power minus 5. So for this concentration of 0.5 molarity, the susceptibility of the MnSO4 solution is obtained as equal to 0.713 to 10 power minus 5. So this is how we measure the susceptibility of the given solution. And same experiment we can repeat for different concentrations of the manganese sulphate solution. Okay, but in all the cases, what you observe is that this power 10 power minus 3 comes. So that is a very, very important point. Only this value will slightly change, but this remains constant. 10 power minus 5 order will remains there in all the calculations. So this is how we have to do the susceptibility measurements by using this virtual lab. Thanks for watching.